So homework assignment was search.
Mm-hmm.
So take in a payload and return true if it's found, false if it's not, something along those lines. You had a couple of different approaches you could have taken with this. We've already done tree traversal stuff. So inside of our binary tree, we I prototyped our search method. So it takes in a value, returns true if the value is in the tree, returns false otherwise. All right, well, how are we going to deal with this? Well, the very first thing we'll do is we'll check our own payload, right? Make sure it's not there. Remember at the end of class last time we talked about kind of a telephone book search, called a binary search. So we'll first check, the whole thing, you put your finger right there in the middle. You say, is this who I'm looking for? If not, should it come before or after this? Rip the telephone book in half, blah, blah, blah. All right, so we'll say,
Do you want to check if it's empty first?
We can. So if this dot is empty, return false. So that'll be our little catch-all to see if there's even a tree to search. Otherwise, if this dot payload is equal to the value we're searching for, return true. Else, we need to determine if it should come to the left or to the right. If value is less than payload, wouldn't be equal to it, but you could have asked if it was equal to it. If it's less than payload, we're going to check the left, else check the right. Okay. Checking the left means what?
Checking to see if the left node is null.
Okay, first checking to see if it's null. So if this dot left tree actually we need to check to see if it's null.
Yeah.
If it's equal to null, return false. Else, we need to actually check that left tree. So this dot left tree dot search value, and we're going to return that.
That's what we missed.
Okay. Otherwise, if this dot right tree is equal to null, return false. Else, return this dot right tree dot search value. So right off the bat, do we start seeing the advantage of treating our tree as a collection of trees as opposed to a bunch of nodes? Okay.
You have to return false at the end, the very, very end.
Well, if this is true, we're returning false. Otherwise, we're definitely returning something there. Definitely returning something in there. Well, I don't think so. I think we're guaranteed to return something here. Okay, so that should be a reasonable solution to the homework. We can test this in driver. So we added a bunch of things. Let's do a, here I'll take out our displays. Let's do our system.out.println bt.search for 9. Do that first. That should give us a true. And then let's search for 240. That should give us a false. True, false. All right, questions about that? So should have been a little bit easier assignment. Everybody do all right with this one? Okay, so The next step here, when we're dealing with trees, we're going to start transitioning away from binary trees and into some other trees, but only after we look at a potential problem with binary trees. Anybody want to take a stab at what a weakness of binary trees is as we've learned it so far? Go ahead.
Efficiency.
Okay.
Take time.
Huh?
Take time.
Okay, tell me more. Why?
Because it kind of has to go through each one to find out everything below it. Like in arrays, you could go right to it, and then linked list, you could kind of like choose a side to go through.
But think about the purpose, though. If you're searching an array or searching a linked list, it's going to be slower than searching a binary tree. Binary tree, we're able to jump through our data to get kind of to the point where it is. So we're really cutting our data in half with each step. So searching binary trees are better. What's a weakness of a binary tree?
If you want to get like the last one you added, there's no way for you to really do that unless you. Right, there's no easy way to get it in the order that you put it in. So if you want,
You mean retrieve it from the tree?
Yeah.
Okay, so and it's kind of the same answer. Is we wouldn't use binary trees for that.
Well, yeah. I mean,
So it wouldn't be the right tool for the job. And okay, that's fair enough. You know, is that really assuming we're using binary trees for kind of the searching, the job that we're using it for? What's a weakness? I mean, certainly, if it's not the right tool for the job, you can't use a wrench for a job that's made for a chainsaw, unless you really swing hard. Good.
Well, one thing with them is we use recursion a lot with binary trees. So
Okay.
that can be memory inefficient. Not that that's really a problem anymore.
We actually don't use recursion.
I thought we didn't. Oh, maybe not.
Remember, every single time I refer to it, I say recursive-ish.
Oh.
Right, because we're not actually putting things onto the stack because we're calling somebody else's method with the same name, just like we're doing here. We're not calling the same tree's search method. We're calling either his left or right tree's search method, which does block, so this guy's put on hold, but he's not thrown onto the stack. Did you screw something up?
No, just some random Mac function.
Just messing up a quiz there or something.
You're working on quizzes in other classes during my class? Are you lying? Before you've even answered?
Totally.
Shouldn't you be paying attention? You're not that great at this stuff. So why don't you answer my question then?
Which question?
The one I just asked.
I missed it.
What I should do right now to punish him is I should have a quiz
on what you just
You're asking why we
telling me what my question was. Wouldn't you feel like an idiot missing that quiz?
Well, I got the main question right.
Okay, what's the main
You're wondering
question?
Why it's inefficient.
Well, I didn't say inefficient, but what's wrong? What's a weakness of binary trees when we're using them for their job? What's the job? You know, what are binary trees built for? What are they kind of good at?
Storing organized information.
Okay, why would we want to store organized information? Why do we organize things?
So that it's easy to search through.
Yeah, so we can find it later. Same reason we organize things in real life, right? Okay, so so for the purpose that a binary tree was built for, why is it weak? He's probably getting nervous because it's probably a timed quiz. Is it?
No.
So let's go run some laps. So,
I would pay to see you run labs. Actually.
you'd actually be surprised. I have shockingly better endurance than you think. So I used to be a pretty big athlete before I broke my back.
You should come run the lakefront with me. You know what you're doing?
Well, I wouldn't do it by choice.
Marathon?
The bigger issue I'm going to have running is going to be joint issues, given the fact that I'm basically carrying the weight of a bear. But I do actually have shockingly good endurance. My cardiovascular system's pretty good. I didn't really lose that. Like swimming, I can swim maybe a couple of miles before I actually get tired.
That's one thing I can do where I join
Yeah.
so hard.
Very buoyant too, so even if I get tired, I could just stop.
Get on the raft!
Yeah, guys are always like because I'm a big golfer and walking, they're always impressed. I go out and I walk 27 or 36 holes in a day. As long as I keep myself watered, like a camel, I just keep going.
So wait, if you get a boat, you never have to worry about a life vest.
It's true, I'm buoyant.
Yeah.
And I float head up.
I mean, you just yell at everyone, get on the rail.
Yeah, because of the way of all my body fat is kind of centralized in the gut. Like I don't have like fat people arms or fat
It's like
people
wearing
legs.
Wearing an
I
inner
just
tube. You got an inner tube on.
right. I'm wearing an inner tube. It's like the little kid with the floaties. Let me see. It was not recently, right?
No, that wasn't That's My Boy.
Oh, right. I just saw it recently. That's why I was thinking it was real news. He won it, didn't he?
Yeah.
Didn't they bet on him like it was like 1,000,000 to 1 odds or something? All right, you're gonna answer my question. You want a hint? I'll give you a hint.
Okay.
Are you still working on your quiz?
I'm working on building a quiz.
You're building a quiz for what?
Different class.
Why are you working on a different class?
Different class.
Not my class. I wouldn't give busy work to build a quiz.
Right.
All right, so here's the hint. You ready for your hint? Okay.
Something to do with inserting them.
Well, it's related. It's related to how things are inserted. If I put 10 elements into a tree, so pick your favorite 10 numbers and put them in it, write them down on a piece of paper. If I add them to the tree in different orders, will it produce different trees?
Yes.
It will. So are all trees created equal?
No.
What would you consider to be a bad tree? Or, in your words, a potentially inefficient tree? Let's let him take a stab first, since he's not paying attention to my class. Kind of visualize.
Ideally, wouldn't the information or the data be added in order?
It's added in an organized fashion. It is organized. So that means everything to the left of the root node is going to be less than or equal to the root node. Everything to the right of the root node will be greater than the root node. But if you add stuff in a, let's say an unlucky order, okay, you add your 10 values in an unlucky order, you could be left with a really, I've given you almost the entire hint so far. I'm about to give you the punchline.
Yeah, isn't there like a perfect tree and then a hodgepodge mess tree
Okay, what's the hodgepodge mess tree?
where it's just added in a random order?
No, we're always binary trees. We're talking binary trees. They're always in a reasonable order. They're always added with that rule. Everything to the left of the root nodes.
I understand that, but like, if it's going to the left, wouldn't you want the numbers to actually make sense in order? I mean, I know you can build a tree and the branches match up correctly, but I'd have to draw it out. But like, wouldn't you want the smaller numbers be added that you start out with a larger number, add a smaller number so that you get a left tree, smaller number, left tree, just keep working that way instead.
Otherwise, what happens? Let's say you add your numbers in the worst possible order.
Yeah.
Okay, we're just you unluckily get numbers that just produce a tree that looks like crap. What would that tree look like? What would a tree that looks like crap look like? Okay, tell me about that. If he gets this right, you should feel like an idiot. Go ahead.
I was going to say it's going to be unbalanced. It'll depend on the insertion of
What do you mean by unbalanced?
all of them moving more to the left of the tree.
Hey, like the tree might have a zillion nodes on the left and like one node on the right. Okay? And what if we're searching that tree? Does that hurt our search?
It'll take longer.
It'll take longer because we have to ask more questions. If we happen to luck out and the answer is either the root node or that one node you have to the right or your one tree you have to the right in our current implementation, then you're okay. But if it's less than our root node, you might have to go down these, ask a zillion questions. Is you're going down this really skinny tree over on the left. Maybe the worst case is when you have everything is left. So you add the things in descending order. So 10, 9, 8, 7, 6, 5, 4, like that. So it just keeps adding it as the left node of the child. So you're left with a tree that basically looks like a linked list. Does that make sense? So then to search that, you're just traversing a linked list essentially, which kind of takes out all that efficiency built into a binary tree. Okay, so given that, we might want to look at ways of keeping our tree balanced. So I'll just throw out there a definition of a balanced tree, and we're going to kind of swing back on this here in a few minutes. Because now I would say this is the point where this course starts getting hard.
Now it gets hard.
Oh yeah, everything we've done at this point has been trivial.
Does that mean we'll get less assignments?
Oh no, I might give you larger assignments each class.
Fewer.
No, but still every single class.
This is less than half an inch.
Okay, so a balanced tree. This is a tree where the left and right side have at most one depth level difference. Okay, and what I mean by depth level, this would be depth 0, depth 1, depth 2. So as we have this drawn, this is a balanced tree, right? This guy has depth level 2, this guy has depth level 2, so the far left, the far right node have the same depth level. Balanced tree. Even if we throw a 9 in here, still balanced, right? Yes, this guy's a little bit longer, but we're within 1. You can only mess around so much. One of the things we're going to talk about in terms of rebalancing a tree is that it's very expensive. So you don't want to rebalance a tree too often. While we might be able to go and reorganize this tree in such a way that it's perfectly balanced, would you say that a tree like this likely doesn't really hurt you? It likely doesn't really hurt you because it's only off by 1. We're not dealing with that worst case scenario where we're traversing a linked list, right? Okay, so not the end of the world. But you start getting 11, 14, so on and so forth. We can start seeing this get out of control. That makes sense? Okay, so that's where we talk about tree balancing. So one thing we want to add to our code right now is the ability for a node to know where it lives in a tree. Okay, this is something called lexical address. Lexical address. Fancy word for saying, where am I in the tree? Okay? So if I ask you on a quiz sometime soon, what is lexical address as it relates to trees? A perfectly reasonable answer would be where a tree is in a tree, or where a node is in a tree. Same thing. Okay? This is our fancy way of saying what's my depth. All right, so now what we want to do is we want to augment our add method so that every single tree, since we kind of got rid of nodes in our current implementation, does everybody understand why we got rid of nodes? It's not that the node implementation is bad. It's kind of in preparation for where we're going now, where we're seeing this ability to kind of recursive-ish call things. Think of a tree as a collection of trees, that type of thing. So it really just kind of makes more object-oriented sense to deal with it as a collection of trees rather than a collection of nodes. But the nodes isn't an incorrect solution. It's fine. All right, so we're going to add to our add method the ability for it to know what its lexical depth is. All right, so we're in binary tree. I'm actually going to kill off nodes since we're not using them anymore. Okay, well, by kill off, I just closed it. I didn't actually remove it, but whatever. Okay, so we'll go down to our add method. I'm going to do something here. somewhere in here there's a handy thing I wanted to show you, but obviously it's not that handy. There's a way to say collapse all methods.
Oh, I remember you showed us that in, I think it was 440. I just can't remember how you did it. Was it in here?
You have to highlight everything to do it.
Showing breadcrumbs.
Yep. Not sure. Used to be. Well, I say used to be.
It's gonna bug me now because it was so easy when you did it before.
Format.
I don't think so. In fact, that broke my formatting.
It's a format.
Let's clean up.
Oh, it like adds override tags and stuff, like things that make it more efficient during compile time. Seems like it should be under source. We can tell it to sort members, so it'll put it in alphabetical order. Oh well, if you come across it, let me know. Not that important, but it goes through and oh, I can't. Oh, it goes through and basically does. Like, maybe it's this. Is that a collapse all? No, but it goes through and collapses everything like this, so it makes it easier to search through. Not that big a deal.
Oh, I found it.
Where was it?
Go all the way over to the left, like up by the numbers. Right click, go to folding. No, to the left.
To the left.
Oh,
Where the number
number
line,
line.
where the lines of code.
Whatever the Mac stuff is, I don't know what
No, go all
the
the way over to the
symbols
left.
mean.
All the way left. This guy?
There.
Yes.
Right click, go down to folding.
Oh, then collapse all. There we go. Thank you.
Shiny.
All right. So what we want to do is we want to go down to our add method. And when we're adding a value, we need to remember the lexical depth of each value. Now, a value is actually represented as a tree, correct? So that means that in our tree, we need to remember private int depth. All right. And when a tree is first created, it's not going to have a depth. But what I'm going to do is I'm going to set depth to default to -1. Okay, that's going to be our default value for depth. We could initialize it up here like that, or we can initialize it inside the constructor. This dot depth is equal to -1. Kind of a illegal depth, if you will. Okay, we know we're going to set it. So now down here in add, when we add something to our list, if we're dealing with the empty tree, or add something to our tree, when we're dealing with the empty tree, we set this tree's payload equal to something, we set isEmpty to false, and we'll set this dot depth equal to 0. And we're going to see that this isn't quite good enough yet. And we're going to actually see the weakness here in a second. All right, so we get to the else. That means we're not dealing with an empty tree. So what do? We say if the value should come to my left side, if the thing I'm adding should be to the left. If it's the empty tree, create a brand new binary tree and set that, add that value to that binary tree. That make sense? Is it the value that has a depth or the tree that has a depth? It's a tree that has a depth. So what we're going to do is we're going to have our constructor for binary tree take in a depth when it first gets built. That makes sense? It'll take in a depth. Now what I'm going to do is I'm going to actually create a second version of this constructor, one that takes in nothing. Okay? This guy's going to take in nothing. And what's he going to do? He's going to call his own constructor, passing it a 0. That makes sense? So this is actually going to support the person out here in driver not having to build a binary tree, initially passing it a 0. When they call a binary tree, they're going to like, why am I passing it a depth of 0? When you're, as a user, when you're originally creating your binary tree, you don't care about depth. You are expecting the binary tree to work well on its own, correct? So you want to build a binary tree this way. And when you first build a binary tree calling its constructor like this, what it's going to do is it's going to call this constructor. So we have two separate constructors to take a different number and or type of parameters. What's that called? Polymorphism. So when we happen to call the constructor that takes nothing, we're assuming this is the first one. So we'll go ahead and call our own constructor, passing it 0 for the initial depth. Okay, this is similar to when we talked about inheritance, calling our parent's constructor to do something. So this is how we call our own constructor. Okay, so we have a constructor that takes in a single integer, and we're calling that one right here, passing it a 0. And what we're going to do is we're going to set this dot depth equal to depth. That makes sense? Now from this point forward, every single time we create a new binary tree, we can call upon this particular constructor, the one that takes a depth. We're using that one internally. In fact, we can make that constructor private. That makes sense? So this constructor is meant to only be used within the binary tree class. This one is meant for our public to use. So when a public first builds a binary tree, they'll build the plain Jane generic binary tree, and internally we get the ball rolling by calling the constructor that takes a 0, the initial depth. Okay, now from this point forward, every single time we internally create a new binary tree, either for the left tree or the right tree, we will use this version of the constructor, passing it a depth that is one larger than our own. Okay, so down here in add, when we create a new binary tree, we're not going to call the default one. We're going to call the one that takes in a depth, and we'll add 1 to whatever our depth is. Make sense? Same thing here. Okay? So again, we're leveraging recursion. That's it. Now every single tree knows about its depth. Just making those couple of changes. Whenever I create a brand new tree, either for my left tree or my right tree, I build it using the constructor that takes in a depth, and its depth will be 1 greater than my own depth. And note that after we create the tree, we try to add the value to that tree. That'll call this method again. So the first time through, that'll be a tree that has a depth of 1. If he's creating another tree, the tree he just creates has a depth of 2. Go ahead.
Did you just do this dot depth plus plus, or no?
This dot depth plus plus. This dot depth plus plus will actually increment the value of depth. It'll make it 1 larger than it used to be permanently. So that this dot depth plus plus is equal to this dot depth equals this dot depth plus 1.
Okay, so you just
We don't want that.
you just want to add 1 to it.
We're creating a number that's one larger than our depth. And we're passing that number into the binary tree we're about to create.
Okay.
So to kind of show this in the picture here, depth 0, when he creates his left tree, it'll be 0 plus 1. When he creates his right tree, it'll be 0 plus 1. So these guys have depth 1. When this guy creates his left tree, it'll be 1 plus 1. This guy has depth 2. When this guy creates his left tree, it'll be 1 plus 1, depth 2. 1 plus 1, depth 2. 2 plus 1, depth 3. 3 plus 1, depth 4. 4 plus 1, depth 5. That make sense? Your question about whether we can say this dot depth plus plus would have said that we're actually making this guy depth 5. And this guy will also be depth 5 because we'd be changing his depth here locally. Does that make sense? We don't want to, when we build our new tree, we don't want to alter this guy's depth. His depth is 4 forever and ever. Well, I say forever and ever until we start dealing with AVL trees where we actually rebalance trees and their depth changes. But for right now, that's his depth forever and ever. Okay? Now what we want to do, well, for starters, does this make sense? How this guy works? And we'll see that our code still works the way it worked before. We didn't break anything. We're just keeping track of one additional piece of information. Every tree knows about its lexical depth, or just its depth. Lexical just makes us sound smart. Right? All right. So now what we're going to do is let's deal with our visit in order. Let's go back out here. BT dot display in order. Okay, so that gets us our full tree in order here, right? Okay, so when we display, what I want to do is I want to actually display the lexical address. So we're going to display the payload as well as the value, or the depth. Okay, so we're going to teach our binary tree. When we print something right here, we're not just going to print the payload. We're going to print, let's follow it by a colon. That looks legit. We'll pass this dot depth as well. All right, that's visit in order. Yeah, visit in order. So now when we run this, we'll see all the depths. Except that's not what I was expecting. Not what I was expecting at all.
Is it because it's still in the same? It's because it's still in 0, isn't it?
It shouldn't have been.
But you're not changing the depth. So the depth in the first binary tree is going to still be 0.
Well, right, but every single time we call that add method,
Yeah.
these guys should get added with a new depth. Let me just do this real quick. It's possible my constructor call is not working right. I need to make this guy public again. Ruh-roh. All right. All right. So that's fine. That's fine. Every single time we add, actually, that might have been the issue. No. Whenever we, oh. I'm setting the depth to 0. That was before. Remember I said you'd see there's a problem? When I put the depth equals 0 and I started going off on my tangent, well, I never went back and took that out. All right. So we see all of our depths now. So we have a depth of 4, we have a depth of 4, a depth of 4. So the deepest this guy ever gets is 4. Now, one thing we don't know, though, is what the depth is on the left or the right. So we need to be able to go down and find the left and right maximum depth. that make sense? Okay, so when we're looking at our tree, if our tree looks like this, we want to get 0, 1, 2. We want to know the maximum depth of the left is 2. The maximum depth of the right is, that's 1, 2, 3, 4, 5. We know we have a problem. That make sense? Let me ask you this. Will the maximum depth on the left always be the far left? Can we create a scenario where it goes deeper over on this way? Sure. Similarly on this side? All right. How do we determine the maximum depth of the left and the maximum depth of the right? Essentially, how do we ask is balanced? We want to have a method that asks whether or not this tree is balanced, now that we're keeping track of the depth of every single node. Go ahead.
You can find the difference of the depth of each side, and then if it's within a certain number, then...
Okay, how do we find the depth of a side? How do I find the depth of the left side here, let's say?
Make a function that finds the depth of the left side.
Okay, tell me more.
Similar to what we've been doing, but like have it exclusively visit the left side.
Okay, so instead of doing an in order or a post order type thing where we're visiting the entire tree, we want to literally walk just the left side. Okay, well, how do we know when we're done with the left side? So if our tree looks like this,
If you search just the left side, won't the left and the right of that one be equal to null?
say this again.
Like, once you get to the end, the left and the right of that node, those two trees would be equal to null.
Oh, so like this guy, he'll have a left and right. So we know we're at the deepest right here. But what about over here? Go ahead.
If we use the search function that we made, but don't actually like try and search for something, just use that idea to search through the entire left side of the tree, and then just hold on to whatever the highest depth we find is, and then do the same thing for the right tree, and then we'll have the two highest.
Okay, what would you search for? Yeah, we're going down a decent path now, but what would you search for to ensure that you visit the entire tree?
I mean,
What value? Essentially, you want to search for a value that you know is not found.
Yeah, you want to search for
right?
like negative 2 billion, but
Hopefully,
Yeah.
or hoping that negative 2 billion is not in the tree.
yeah, but there's definitely, I think there's a way to do it without needing the...
A search value.
Yeah.
Okay, so we're not failing out when we have true or false. We're just continually traversing the tree, checking every single thing. We're essentially doing a visit, an in-order visit of everything on the left. And actually, it doesn't really matter which kind of visit we do, as long as we visit every node, right? So let's go into our binary tree. We'll write a method here, public Boolean is balanced. Okay, and this guy is going to return true if the tree is balanced, which means it's within 1. Maximum depth is within 1 of both sides. So first thing we're going to do is get the depth of the left. So let's do that. So we can start off with, well, we can actually do this. If this dot is empty, return true. Balanced tree, right? Okay. We're actually going to see that this might be problematic in and of itself. Okay.
Wouldn't you think it's balanced if they're
Well,
aware of this?
maybe. Depends how we use this Boolean. Because as you might guess, we're probably going to have some recursive-ish stuff going on here, right? Okay. So we'll go on to the else.
But then again, that is empty only works if there's actually tree there.
Yep, just roll with it for right now. Okay, this just is going to protect us for that very first call. So now we're into else. We're going to deal with what's the depth of the left side. Okay, so we know that we're currently sitting at depth 0. So int cur depth is equal to 0, or cur max depth. Cur max left depth. Can we just keep adding on to that variable name? Okay, so cur max left depth is 0. Man, if you can't say the variable name, you shouldn't be using it. All right, so now, while what? We need to get this guy's, well, maybe we use a while. Let's go this route. I need to traverse the left side here. So we're only going this direction. So in this particular case, I'm sitting right here, and I've decided it's not the empty tree, so I need to find out the maximum depth of the left-hand side. All right, so the first thing I'm going to do is I'm going to get the depth of my left to start the ball rolling, right? And get the depth of my, well, the second one will be get the depth of the right when we go check the right side. So I want to be able to ask a tree to get its max depth. So public int get max depth. And actually we can make this private. We're not going to call that externally to this. We're probably also going to make our isbalanced private. But right now we'll actually, let me just make them both public right now. That way we can call them from driver just to test them. But then we'll make them private because we're not going to be directly using them. So get max depth is going to start at the current tree, whoever we called here. And this guy is going to return the maximum depth of the tree, the nodes beneath him. That make sense? Okay. How do you do that from a tree's perspective? What is the maximum depth? So we'll go back to this guy here. If I'm sitting at this node and I want to get well, if I'm sitting at this node, I want to get my maximum depth. How do I do that? Okay.
Getting its next left one until it's equal to null. Until its next one's equal to null. That'd be the deepest depth for the left.
Okay. Now remember, each of these is a tree, right? So that's why I notice I'm not starting with the root node in this particular case. We could certainly start with the root node. If we're trying to solve the problem, the mental problem of get max depth, and I started with the root node, this guy is going to return the maximum depth, which will be this guy. That's what we ultimately want him to return. Make sense? But that doesn't help us with isbalance, because with isbalance, we need to know the maximum depth of the left and the maximum depth of the right. But for right now, we can think about this as the full tree. Because all we're solving, the one problem we're solving right now, is get max depth. So if this is my tree, how do I get the max depth? Started right here. I'm going to call get max depth on this tree. Well, is it fair to say that the maximum depth of this guy is the maximum depth of his left and right tree, 0 plus that? Is it fair to say that the maximum depth of this guy is whatever is his depth plus the next tree down? Can we just add? We don't have to ask about their depth. Can't we just add their depth? As long as there's a tree. So is this 0 plus 1 plus 1?
Would you be able to, for getting the max depth, would you be able to use like visit in order and just increment each time it visits each node?
You could, but don't think like that right now. I'm trying to teach you to think recursively for this problem.
But the problem I see is then, so what happens if you have that tree, but then there is let's say another tree off of the one and then another tree off of that one. Because then once you go 1, 1, and then if you go back and do the other 2, won't that add an extra 1?
Well, not if you add an extra. What do you mean add an extra
You're
2?
just adding 1 for everything that you see.
You're going to have to check the maximum of each of the left and right each time through. Okay. So that's why we're saying the max depth of this entire tree. So if we look at this guy, we're asking what's the max depth? Ultimately, we want the max depth with it. 0, 1, 2, 3, 4, 5. This guy should return 5 for get max depth. This entire tree here has a maximum depth of 5. Because what did we do? We compared the depth of his left side, which is 0, 1, 2, to the depth of his right side, which was 5. Make sense? So we're getting the maximum depth of each of these sides. The maximum depth of this side right here is what? It's the maximum number of this or this. So this is 0, 1, 2. This is 0, 1, 2, 3, 4, 5. Which is bigger? 2 or 5? 5 bigger, right? Okay, so if I get the depth of this side here, this subtree, we can look at this guy as a tree. The depth of this guy is going to be the maximum of these two. Between this node, which is the far left branch, and this node, which is the far right branch. That make sense? So at each point in time, we're going to return the maximum depth from these two. So when we're in get max depth, we're going to say if for every tree, he potentially has a left and right node. Correct? So if this dot left tree is equal to null, and this dot right tree is equal to null. If I don't have a left and right tree, then I'm going to return my depth. From my perspective, that's as far down as I can go. Okay? Else, if this dot left tree is equal to null, then I'll return this dot right tree dot get max depth. Else, if this dot right tree is equal to null, I'll return this dot left tree dot get max depth. Else, okay, else we are dealing with something where we have both a left and right tree. So we want to return the maximum value of our left and right tree. Make sense? So we're going to return math.max this dot left tree dot get max depth, and this dot right tree dot get max depth. So math.max just boils down to the greater of these two values. We could have certainly written that method ourselves, right? If this number is greater than this number, return this number. Else return this number. Make sense? So this isn't doing any sort of crazy magic. It's just comparing two numbers, and it's a nice little convenience function for us. So math.max gives us the maximum value of two integers. There's also a math.min. All right? So if we don't have a left or right tree, our maximum is our self. If we don't have a left tree, our maximum will be our right tree. The max depth of our right tree. If we don't have a right tree, our maximum will be the max depth of our left tree. Otherwise, it'll be, if that means we have both a left and right tree, we're going to return whatever the larger of the maximum depth of our left and right. Make sense? That's what max depth will do. Notice that eventually, and this is kind of what Curcio was saying, eventually we get to where we have a left and right node that are, or left and right tree that are null. That's when we finally say, this is the deepest that I know about. Okay? Now inside of isbalanced, you know what? I'm going to, just so I don't forget to make them private, I'm going to make these guys private right now. I'll just print out within them. Oh, actually, I'm sorry. Isbalanced needs to be public. Well, just whatever. Get max depth will definitely be private. I will actually be making isbalanced private as well because we're going to be using isbalanced as part of the AVL rebalancing algorithm that you'll be doing for homework. And I tell you, it is a nightmare.
Wait, go back. Wait.
Yeah. No, see, now you're distracting me, so I don't go very fast. Any way you cut it, you're researching it on your own and doing it. That way I don't have to give you homework over break.
That's Google.
Right? It's a fair trade-off, isn't it? No homework over Easter break, but you're going to have to do a nightmare assignment for Thursday? It's fair.
Probably less of a nightmare than my 440 stuff for you.
What was I talking about?
Nightmares.
Me crying when I look at the homework.
All right, so isbalanced. If we're dealing with the empty tree, isbalance is true, right? It's true, right? It's true. Otherwise, I need to get my cur max left depth, and I need to get my cur max right depth. I'm going to take that comment out. And I'm going to copy this line. And this is going to be named right depth. Now, remember, we're going to be calling isbalanced on the top level, the top of the tree. How do I get the max left depth and the max right depth?
Get max depth.
Okay, get max depth of who?
The left tree.
Left tree and the right tree. Okay, provided I have a left and right tree. Okay, so if I have a left tree, its max depth is get max depth of the left tree. What if I don't? Max depth would be 0. All right, so here I'll show you. I think I've shown you this before, but this is a kind of a fun way of writing this. I'm going to say this dot left tree equal to null question mark 0 colon this dot left tree dot get max depth. So a fun little line.
I like it.
Similarly, this dot right tree equal to null question mark 0 colon this dot right tree dot get max depth. Have I shown you the syntax before?
No.
No.
Are you lying?
No, I haven't. I like it.
Is a question mark just asking?
Huh?
Is a question mark like asking?
This guy is known as an inline if statement.
Yeah.
This is an inline if statement.
Okay, so it's saying.
Okay, so this is my Boolean expression. I'm asking this question. If this boils down to true, boil down to that value. It's really only good for numerics. Okay, so if this is true, this entire expression will boil down to 0. Otherwise, this entire expression will boil down to whatever this guy returns. It doesn't let you do multiple things. It's kind of like a one-off. Okay, so this is a good way of kind of doing these null tests,
That's
kind of inline.
a shorter way to write something you're already doing that's relatively simple.
Yeah. So does this kind of make sense? If I were to give you the kind of the generic syntax for this, it would be Boolean expression question mark true val, colon, false val. Something like that. What's a Boolean expression? Any expression boils down to a single value of true or false. All right, and that kind of makes sense. So, like throwing in some little more advanced structures like this. If you don't like this syntax, you never have to write it. You can just put a nice little if statement in there that says, if a left tree is equal to null, cur max left depth equals to 0. Else, cur max left depth is equal to this dot left tree dot get max depth. Does the exact same thing.
Would it not do that in max depth? Well,
Who?
would it not do that in max depth?
What do you mean?
So if it's equal to null, it wouldn't put it to 0.
Well, I'm only calling get max depth if this was was false.
Okay.
This is my false statement. This will never get called if it's null. Okay, so if I'm writing the equivalent here, I'll just write it right underneath it. If this dot left tree is equal to null, cur max left depth is equal to 0. Else, cur max left depth is equal to this dot left tree dot get max depth. So that code right there is equivalent to this line right here. They do the same thing. That makes sense? So it's called an inline if statement. It actually comes from the C programming language. So kind of a toss back. Maybe a lot of Java programmers will never use this because they never saw it. It's probably not in Java textbooks. It's kind of an old, I guess an old trick. But certainly handy in situations like this. All right, questions on that? And I would never require you to write an inline if statement. So you'll never be quizzed or tested on what's an inline if statement and how does it work. It's more of a trivia thing. Just add it to your toolbox. If you like it, great. If you don't confuse yourself with it. All right. So we have our cur max left depth and we have our cur max right depth. And we'll go ahead and print out system.out.println max left is equal to cur max left depth. And then we'll print out max right. This is just for our own visual. Is cur max right depth. Okay, but ultimately we need to return a true or false. And I want to return true if, true if the max depth is within 1. The max left depth is within 1 of the max right depth. How do I do that?
Saying if you might need 2, but if the cur max left depth plus 1 is there.
So this will take the absolute value of the difference. Math ABS cur max left depth minus cur max right depth. So it'll either be a negative something or a positive something, right? But this is going to give me the absolute value of it. And as long as that is less than or equal to 1, we're true. Make sense? So here's another math function you can use. Get the absolute value of something. As opposed to asking if it's less than 0, multiply it by negative 1. All right, so this will just subtract the max left depth from the max right depth. If you like it, you can flip those around. Doesn't matter because you're taking the absolute value of them. Okay, and then you're just comparing that to 1. If it's less than or equal to 1, if the difference between those depths is less than or equal to 1, we're balanced, therefore return true. If it's not less than or equal to 1, that means it's 2 or greater, we're not balanced. This guy should return false. Make sense? All right, so out here at driver, we're going to go ahead and say bt dot is balanced, so we'll call that. Here, I'll print it as well. That way it gives us the true or false. Okay, so bt.isBalanced internally is going to tell us the left and the right depth because we printed that inside here just for our own records, just to see it. But then it's going to return the true or false whether or not it's balanced. Go ahead and run this. Max left is 4, max right is 4, so it is balanced, true. All right, so let's do this. Random r is equal to new random. We'll just add numbers between 0 and 250. It could certainly be negative numbers. You know, actually, we'll just give it the range of all integers. That's negative 2 billion to positive 2 billion. So we're going to randomly fill up our binary tree with 500 random integers between negative 2 billion and positive 2 billion. Pretty decent chance we're going to end up with an unbalanced tree. Okay? Could luck out. Decent chance. Okay, when we're adding 500 of these. All right, so we'll add those, and then we're going to print out our isBalanced. So we'll see what we end up with. All right, max left was 14. Max right was 17.
That's not bad at all.
False. First of all, something that should be of interest to us, notice that we added 500 values, but only had to go down to a maximum depth of 17. That means a lot of our values are centered in the middle. What does that kind of tell us about the distribution of the random number generator?
It's not so random.
Well,
It's random.
it tells us it's fairly evenly distributed, right? Kind of a fun 1319, not horrible. 1814. If we get something that's like 1 in 56 or something, that would start being
5 and 18.
Ooh.
Whoa.
That's close.
Sorry, what? For that last one,
what was it?
It was true.
the numbers didn't match up.
It was within 1 though.
Within 1.
Was it?
That's 50,000 numbers. We only have to go down to a depth of 36. Yeah, it's actually tough to represent it graphically in text.
Because there's so many.
5 million?
First one's true.
Is it cooking? It is cooking.
Take off the 0.
Well, 5 million shouldn't take that long.
Just because the range is so great.
I can't imagine it's going to take more than like 20 seconds. here, while that's cooking, I want to bring up Avl Trees on Wikipedia. So it gives a nice graphical depiction of the algorithm. All right, so first of all, Avl trees, it's something known as a self-balancing tree. Okay, Avl trees are self-balancing trees. AVL doesn't stand for anything. Well, it does. It stands for the first initials of the people who created it. Foreign names, I don't know their names.
How do you gotta do that?
Huh?
All the acronyms we have.
Okay, so Avl trees, it's a self-balancing tree, which means after we insert something into the tree, after we add something into the tree, we have to check to see if the tree is balanced. We already have the code to check to see if it's balanced, right? If it's not balanced, then we need to do AVL's rotation, which rebalances the tree right now. And the reason why we consider it balanced if it's within 1 is for performance reasons. If it's slightly out of balance, it's not the end of the world. Okay? So we'll leave it alone. Now, could we actually modify this for certain applications and say that balanced is actually anything within 3? Not the end of the world, right? Could certainly do that. So having a is balanced within 1 is just giving us a little wiggle room. Just a little wiggle room. But certainly if we say 2 or 3, that's still a fairly balanced tree. Okay? So AVL trees will check to see if it's balanced every single time we insert a value into the tree. And if it's out of balance, then we fix the tree. We go through some steps to rotate. That's what you're going to be doing for your homework assignment. So we're going to talk about it here. Okay, and notice AVL trees are just binary trees, okay, from an organizational perspective. The concept, though, is searching a binary tree. Searching a balanced binary tree is far more efficient than searching an unbalanced binary tree. It's the nature of the beast. Okay? So here is our situation. Can I actually just bring these graphics up? Can I make this? Very, very handy. So exciting.
Next to the screen on the right side.
It's actually funny how as I
Minimize it gets bigger.
yeah, we'll just leave it. Oh, I can do this.
Oh. Hey.
Allow. Okay, so in this example, we've just added a node here 4, and that brought this tree to be out of balance. Okay, brought this tree out of balance. So now, what are we doing? We have to rotate this tree up. So this is where things get a little bit cleaner because now we're thinking about them as trees rather than nodes. All right, so what does it mean to rotate this tree up? It means take the 4 and actually make it take the place of its parent tree, where its parent becomes the left node of this guy.
See, that's kind of what I was talking about earlier. You would want it to be in order.
Be in order, what do you mean?
Because it's becoming 543 instead of 534, so it's in order.
Well, that's kind of coincidence in this particular case. I don't think it's necessarily guaranteed to be that way.
Okay.
All right, so we notice it's out of balance, so we're going to rotate the 4 up, which means it goes into the position of its parent node, and then it's it's like a counterclockwise rotation. So if you think about what's happening there, the 4 is going like this, and the 3 drops down and becomes the 4's left node. Okay, see that there? Yep. So we do the counterclockwise, so the 4 rotates up here, the 3 rotates down here. Then we go clockwise. The 4 rotates up here, the 5 becomes its new right node. And now we have a balanced tree. That makes sense? Similarly, if it's the right-left case situation, where we have a node down here, we rotate it clockwise, then we rotate it counterclockwise to get it up into a balanced state. Make sense? You'll have to figure out, what does it mean to rotate? Okay? What does it mean to rotate? They actually do give you some pseudocode here if you want to try to look through that, but I would encourage you not to. All right? Right now, we are not deleting anything from our tree. So you only have to deal with the rotations during adding, when we're putting something into the tree. That make sense? Okay. Now, one more thing I'll throw out there, and this is more of a trivia thing since we have a minute. You may have heard of something called B trees before. Okay, B trees are not binary trees, not to be confused. Okay, a B tree is also a self-balancing tree. These are typically used in databases. Think about the job of a database. A database is actually storing most of the stuff on disk. Okay? You're not searching through memory for data in a database. You're searching on the hard drive, on the disk for data. You know, because the idea might be you might have a database that has 500 gigabytes of stuff. Hard drives are big enough to hold that. Memory is not. Make sense? So B trees, each subtree, or each node, however you want to think about it, is actually larger than we've been representing it. What it does is it makes it the same size as a single block on disk. There's actually an efficiency thing. It's related to something we talk about in the operating systems class with internal and external fragmentation or something along those lines. Don't worry too much about that right now. But the idea for a B tree, it's a self-balancing tree, but designed to be done on disk. So each search actually looks within an entire block on disk. That way you're not, because if you think about, a single value, one of our payloads here is really tiny. So if a block on disk is 4 megabytes, let's say, and we have a single 32 byte number, that's not a whole lot of data, right? So if you needed to search through a huge collection of stuff, what you'd end up doing is you'd be jumping from one part of your hard drive to another part of your hard drive very, very, very often. Horrible for your hard drive and also very slow. Okay, hard drives are nowhere near as fast as memory. Even solid state drives are nowhere near as fast as RAM. Okay, so a B tree kind of changes that internal structure of the tree a little bit to store more data at each individual tree. More of an array of payloads, if you will, instead of a single payload. Make sense? Okay, so that's more just trivia information for B trees. They're a lot like AVL trees, just the goal is that B trees are for hard drive storage, so they're usually used for databases, whereas AVL trees are for memory-based storage for searching through things that have been loaded into RAM. All right, so your homework assignment for next class is to make your add method always balance the tree if needed. So if the tree is out of balance, use the AVL tree rules to rebalance the tree. Okay? So the idea is that after each insert, isBalance should always return true. And in the end, isBalance should always return true. If you ran my code right here, no matter how many, did it literally never finish? It ran out of space. Good. No matter how many numbers you're putting in there, it should always produce a balanced tree. Make sense? All right, I'll upload this code to GitHub. Remember, today's Bible study day, free lunch, go to the cafeteria, then go down to the terrace room, blah, blah, blah.
The slides, have you had a chance to update those on there? Because last time I went to try and pull the slides, they weren't updated.
See, it should be updated. It's like iCloud hasn't been fixing itself, yeah.